when I need an array, I use a standard vector container, and in many cases I need to know the sorted state of it, i.e. if I've been passed a vector of integers and I need them to be sorted to do what I want to do, have I been passed them already sorted, or do I need to sort them myself? Usually you'll be passed a const reference or a const pointer to a vector, so if you do need them to be sorted, you'd need to clone them and sort them in the way that you want to sort them before you can proceed. But if all that work has already been done, if you've been passed a vector that is already sorted in the way that you want, then cloning things and sorting things is all unnecessary work, and you don't need to do them. So I wanted a standard vector container that knew its sorted state, i.e. has it been sorted, and if so, how has it been sorted? For instance, if it's a vector of people, has it been sorted on age, height, income, any other field that is in the data structure? So that was my goal, to write a vector class that maintains a sorted state, and also some helper classes that, given a sorted state, can find something or find where something should go if you're going to insert something new, or if the sorted state is currently null, i.e. not sorted, can perform that sort. And then these vectors can be passed around. So I get passed a vector of ints. I say I need them sorted, so I say to the vector of ints, are you currently sorted? And they say yes, so we can proceed without doing any extra additional work. An example of the usage of the code that I've written is this vector of ints. So we define the ways in which it can be sorted, so it's just a simple int vector, so it can either be null, which is not sorted, or primary, which is sorted on the integral type, the type of each element in the vector. In this case, each element is an int. So then we write the class. We've called it int vector. We derive from a class that I'll speak about later that does the maintaining of the sorted state. We pass it the type that we want each item in the vector to be, in this case int, and we also pass it the type that represents the ways in which this vector can be sorted. Once we've done that, I've written a clone helper function, and I've also written a clone sort. So typically a function would be passed a const pointer to a int vector, and if it wants a sorted version of it before it can proceed, it could simply call clone sort. Clone sort would say, have we been passed something? Is it sorted in the way that we want it to be sorted? If so, just return what we've been passed, saving a lot of time and saving any indecision about any ambiguity of the state, the sorted state of the vector. If that's not the case, i.e. we have been passed something and it's not sorted in the way that we want, we could simply call clone, which we've written here, and then call sort using our sorter, which I'll speak about in a moment, and then return that. So now we have got a vector of ints that knows about two sorted states, null and primary, it knows how to maintain those sorted states, i.e. when to go from primary to null, and vice versa when sorted. And it also has additional type sorted, which will be used to sort the vector, find something in the vector, and find where something should go in the vector. So we could have a look at this. What do we define? We define the type of the equivalence operator. I'll speak about that in a moment. We pass in the vector type, which is our type. We define a less than operator using the same vector type, but also what sort type does this less than operator represent? Well, in this case it's primary. And then when we've got our two operators, we can define the class that does all the heavy lifting, really. So we define its type as vector sorted. We give it a int vector type, which is us, and we give it our two operator types, one for less than, one for equivalence, and it's the less than operator there that knows what sort type it represents. If you had a data type that represented a person, for instance, you would need to define equivalence operators, less than operators for height, age, income, etc. And you would have sorted, which would be the which would let you sort on the type itself. We would have height sorted, probably called something like that, name sorted, income sorted, and those additional custom sorted types would allow you to find something related to height, something related to income, also sort on those values as well, sort on those fields as well. So how do we and we could have a look at something a bit more complicated, a custom type. So here we've got int pair. Int pair is a pair of integers derived from the standard pair, and it knows whether it's equivalent or less than another int pair using these operators. But if you want an operator that wants to know only whether the first value is less than the first value of another int pair or equivalent, then we need to define additional operators, which is what these are. So that's first, that's second. So these custom operators can help the custom sorted types decide whether or not a value is less than another value or equivalent. And then we've got our int pair sort type, which is null, which was the same for the standard int vector. We've got primary, which again is the standard, is the same as the int vector. So primary would effectively call these operators, and then we've got first, which would call these operators, and second, which would declare these operators. We define the class as being derived from our vector class. Each type inside the vector is an int pair, and the ways in which this vector can be sorted is here we've described as not sorted, sorted on the type itself, sorted on the first int or sorted on the second int. We have written a clone function. We've written our equivalent of the int clone sort. So the int clone sort was just basically, are you sorted on primary? If not, sort and return. Hopefully we are, which means less work to do. So just return what we've been passed. This is a little bit more complicated because there's more than just null and primary, this first and second. So we pass in a sort type that we want. So we pass in a vector, we pass in the way in which we want the vector to be sorted, and we do our simple check, i.e. is there any work to do? Have we been passed a vector, and is the vector sorted in the way we want it to be? If not, clone, which is that function. And then you can switch on the type. So null, we just set the sorted state to be not sorted. Primary, we use our primary sorted class type there, create an instance of it, and then on that we'll call sort, passing it the vector and the predicate operator that represents the less than function. And first and second are the same, but we'll use an instance of a sorter that is specific to the first or the second. So I've called one first int sorted and second int sorted. Now, how did we define these sorters and custom sorters? Well, exactly the same as the int vector, in so much as we define an equivalence operator, and we define a less than operator, and we pass it what sort type value does this less than operator represent. Well, it's primary in this case, because it's going to be using the class defined equivalence and less than operators. And then when we've got those, we define in the same way as the int vector a sorted class type, which is vector sorted, which we'll go through in a moment, and we pass it the vector type, which is our type, the two operators less than and equivalence. So if we just had that, we would have a class called intPairVector that is a vector of int pairs that could be sorted using an instance of that class, or an element within the vector could be found using an instance of that class, or if you was going to insert a new item, the position in which that item should go, again, you would find by creating an instance of that class and using it to find an index. But we have done a bit more than that. We've written two more custom sorters. One is only interested in the value of the first int of the pair, so we define the equivalence operator, and we're going to be using that which we can see we're using there, and we define a less than operator, which you can see we're going to be using that, that only references the first values of the pair. And then once we've got those two operators, we can define the sorter by, again, exactly the same as the int vector, giving it the vector type and the two operators, less than and equals. And we do the same again. We define another custom sorter. I've called it surname. I should have called it second. Oh, it doesn't matter. I must have been thinking of something else at the time. So I've declared an equivalence operator that's only interested in the second int of the pair. for some bizarre reason I've called it surname equivalent predicate operator, and then less than, using the same method, using the class that's only interested in the second value of the int. And then once we've got those two operators, we can define a sorter, again, that gets past the vector type and gets past the two operators, the less than and the equivalence operators. As you can see, the less than operators for all three of these types: the standard, class, the integral type, what I call primary, the first int type, and the second int type, they get past the enum value that represents the way in which the vector will be sorted if you use that less than operator. So that's how to use the class. So you can define a vector of any type. You can define any number of ways in which that vector can be sorted. I normally call the first you have to have null, by the way. After null, which means not sorted, I tend to call it primary. Primary means the way in which the class or the vector element type knows how to compare itself to another instance of that same type, how to know whether it's equivalent or less than. I tend to call that primary. And then after that, any number of additional custom sort types can be used, as long as you define the operators that know what would be an equivalence or what would be a less than test. And once you've got those, you can define the sorter, and then the vector can be used to find something, used to find where something should be put, and also used be sorted. So I will show you a small bit of UI wrapper, an app. This is a dialog app that I used to demonstrate what we just spoke about with the int pair vector. So if I populate, this is one vector of int pairs sorted on the primary. So each less than operator is being called is that one, and each equivalence operator being called is that one. As you can see, it's sorted. And if we change the sort type to first, that's not going to change because it's just the first value of the int pair. So now when things are going to be sorted or attempt to be found and so on, each less than an equivalence operator being called would be one of those two. And then we've got second. So now to sort things, an instance of that class will be used, which in turn knows how to use the less than and equivalence operators that relate only to the second value of the pair. So we could try and find something. Let's try and find 5,000. Again, because we're sorting on the second int, that's that sort type. I'm only interested in the second value. So 5,000 has not been found, but if you was going to put something in using the current sort method, then it would go at 6, which, as we can see, is correct. It's after 4,736 and before 10,774. Same for the first and same for the primary. Also, I've written in the class that we'll go through that does all the work, I've written a diff operator. So we could take this vector of pairs, take out the first values and the second values. So we've got two vectors of ints, and then called diff. Diff will say what's in the first vector only. So in this case, what's in the first column only, what's in the second column only, and what's in both. So that's what you can do. This is a bit of UI that demonstrates what you can do with the vector, with our vector type. You can create an instance of it, you can ask it if it's sorted, you can ask it to find something, you can ask it where something should go if you're going to insert a new item. And there's also a helper function. So if you've got two vectors, you can say, show me all the things that are in the second one but not the first one, and so on. So mainly it's a time-saving exercise. In many of my projects, I'll be passed a vector of a particular type to do what I need to do. I need it sorted in some way, so I can say to the vector directly, are you sorted and in what way? And I can just then save a lot of time by just continuing to use that vector without any cloning or sorting to proceed. So let's have a look how it works. If we have a look at the vector class, the int vector sample that I've written is in the bottom of the class definition itself. So we'll have a look above, and here we go. So this is the vector class. It takes the type of each element in the array, and it takes an enum type, which represents all the different ways in which this vector can be sorted. Like I said previously, one of the values must be null because the vector instantiates itself initially as unsorted. So this is just a wrapper for a standard vector, standard template libraries vector. Each element is of type T, and the sorted state is of type E, and this sorted state is maintained. There's various functions in here to help grow and shrink the array in various ways. The code that actually sorts the array and finds things within it, I've put in vector predicate. So in vector predicate we've got some standard these are the standard operators. These are the standard equivalent of the custom operators that we saw in int pair. So the int pairs less than and equivalents that related only to the first int or only to the second int. This is the generalized version of those. So it takes a vector type. This is the equivalent operator. It takes a vector type. From that vector type we can get the type of each element in the array, and we'll take a left and a right, and we'll say, is the left the same as the right? So now we've got a general equivalence operator. We also take we also have a less than operator, again, which is generalized. So it takes the vector type from which we can get the type of each element in the array, and it also takes a value of a value from the enum that represents how the vector will be sorted if you use this less than predicate operator. And you can get how the vector is sorted from the operator itself. So this is just a standard less than operator. It doesn't do anything spectacular. Sometimes each item in the array will be a pointer, So I've written a couple of general dereference operators as well for equivalence and less than. I've written a helper function called unsorted, which takes a vector type and an equivalence operator type. It takes the vector, the thing that you're looking for. So given the vector, we know the element type of the array, so that's the thing that we're looking for. We are given an equivalence operator, that's the result. Where is it if we find it? And I've written a range class, a vector range class, so this is where to look in the vector for the item. So this is unsorted, so there's nothing we can do really apart from check the range, see if it's valid, and then if we've got a valid range, call getIterator, which like I say, because this is unsorted, it does nothing apart from sequentially go through the range using the predicate operator to find a match and return it if we've found one, or end if we haven't. This is the class that does the heavy lifting for the sorting and the finding. This is our sorted version. Again, it takes the vector type, it takes the less than operator and the equivalence operator, and this has also got a function called getIndex, like the unsorted version. It takes the vector, from which again we can determine the array type, the vector, the thing to look for in the vector, an instance of a less than operator, an instance of an equivalence operator, the result, and where to look in the vector for it. So we can say, have we been given a vector and is it sorted correctly? If it hasn't been sorted correctly, then we'll use the unsorted helper class that we've just spoke about. But if we get here, we've been given a vector, it's sorted in the way we want, we check the range, and if everything's good, let's call getIterator. So getIterator will call effectively get first, not before. So get the first position in the vector whose element is greater than or equal to the thing that you're looking for. So getIndex calls getIterator. GetIterator will then call get first not before, which could return something that's greater than or equal to, so could be equal to, could be greater than. So then we test for equivalence using the predicate operator passed. So if getIterator returns something that isn't the end, then we can use it to get the distance, and we then set up the index using that distance. Get first, not before. So that's used to find something, getIndex. Get first, not before is used to find where something should go. So typically I've got a new item to put into the vector. Where should it go? We check again that we've been passed a vector, it's sorted in the way that we expect it to be. We check the range, and then we call get first, not before, and then use the distance to find where the item should go. So there's the first two member functions. Find something, find where something should go, and then we've got the actual sort. Sort takes the vector type, and it takes the less than operator, and it effectively, well, hopefully you would say it would find that we have a vector and its sorted type is the same as the enum value in the less than operator, which we which we know that we can get because we pass it here, and you'd also need to pass it in any custom one as well. So using this less than operator, get the sorted type. Is that the same sorted type as the current one in the vector? Return. So hopefully you've been passed a vector, you've called clone sort, or you've checked the sort type yourself, and you've found that there's nothing to do, rather than just being passed a vector of values and not know how it's sorted, and so have to clone it, have to sort it, and then know that that might or might not have been unnecessarily complex or unnecessary work that you've done. But if we get here, we know that it's either unsorted or not sorted in the way that we want, so then we call the standard sort using the less than operator that we've been passed. And this is the diff. I showed you the diff. So given two vectors, it finds items in A and not B, B and not A, and items in A and B. This is all going to be on GitHub, so you can have a look at the diff. I won't bother explaining it. You can go through that later on. So the crux of the matter is, really, we have a vector that supports any array type, any element type. It supports any number of ways it can be sorted, and it supports maintaining the way in which it's been sorted. So it knows the way in which it's been sorted. It will maintain that value, and and hopefully it will cut out unnecessary work. So all of this is going to be on GitHub. There's a bit of UI that shows how to use things. It should be straightforward and clear though, really. And hopefully it will be a time saver.